This is Dr. J. Mohan, and today we are going to discuss about the Laplace transform session 4 in the topic of signals and stochastic processing subject. Today presentation headline is time shifting property of Laplace transform, time reversal property of Laplace transform, conjugate property of Laplace transform, time differentiation property of Laplace transform, integration in time domain property of Laplace transform, frequency derivative property of Laplace transform. These are the topics I referred from B. Lathi Signals and System Communication, KV Opnum for Signals and System. Previously we discussed about the property. Then I continue for the next property, that is represented as a time shifting property of Laplace transform. The time shifting property states that Laplace transform time shift of t0 in the time domain corresponding to the multiplication by the complex exponential of e power s t0 minus in s domain. So that means if time shift is going to happen for the x of t minus of t0 in the Laplace transform domain, it's multiplied with the e power of minus t0 s into x of s. So this is represented as a statement of time shifting property of Laplace transform. So if you are going to shift for the minus of t0 in the time domain, in the input case, the output of Laplace transform is multiplied with the e power of minus t0 s into x of s. So we need to prove for the statement. That's why what I am doing, first we take for the Laplace transform of x of t is equal to x of s. X of t of Laplace transform is equal to capital letter x of s. According to the time shifting property, time shift is going to happen for the input x of t minus of t0, take Laplace transform. The output side of the Laplace transform, it's multiplied with the exponential value of e power minus s t0 into x of s. That means this is a Laplace transform domain of system, that is Laplace transform domain of system I call for h of s. So we pass for the input is represented as x of t minus of t0, the input. The output is represented as y of s. That output is equal to how many times shift is going to happen. We should multiply with the t0 of s into x of s. Okay. We need to prove for this statement for the time shifting state of Laplace transform. First, we take for the definition of Laplace transform. Laplace transform definition is equal to Laplace transform of x of t is equal to x of s equal to integration of 0 to infinity x of t e power minus s t dt. This is represented as a Laplace transform of definition in the signal for unidirectional. Now, instead of this t, I should substitute for the t minus of t0. For instead of the input side t, we should substitute t is equal to t minus of t0. Now, I shall substitute for the Laplace transform of x of t minus of t0 is equal to integration of 0 to infinity of x of t minus of t0 e power st dt. So here what the t is there, then I substitute for the t minus of t0 now. Now I should write t minus of t0 equal to u. Okay. Then at the same time I should find for the t also. The t is equal to u plus of t0 and dt is equal to d of u. This is constant, that's why it doesn't get for the any differentiation. We should this all value we should substitute for the this equation. So what would be happen? a Laplace transform of x of t minus of t0 equal to integration of 0 to infinity of x of u. That this term we should substitute here. Here is have the t instead of t. I should substitute for the e power minus s u of u plus of t0. Then dt in terms of du I substitute here. Now I can split this equation for exponential value. What it will happen? So I should write here integration of 0 to infinity x of u, that is small letter e power minus s u into e power minus s t0, then d of u. This term is represented as not related to u. For here see all terms are u for input, exponential value, differentiation value, all. So this is I take it out here. E power minus s t0, integration of 0 to infinity x of u e power minus s u du. So see all terms of depends upon the u. That's a, due to that case I compare with the Laplace transform equation for here. Here what will be having all terms are depends on the t only for here. So I should write for the x of s. Same like that one. I should write for the x of s here. For this term I should write for x of s. Then it will be have the constant. Now you can see the Laplace transform of time shifting in the input side t minus of t0. Then output side what will be happen? How much time duration is going to shift? That much exponential multiplication is going to happen in the output side. So similarly, if I am going to take for the t tends to t plus of t0, we take for the Laplace transform x of t plus of t0 is Laplace transform equal to e power plus s t0 x of s. Okay, it's proved that time shift of t0 correspond to the multiplication by complex exponential value of e power minus s t0 in s domain. So we proved for the time shifting property of Laplace transform. So here I take for some example. Using the time shifting property of Laplace transform, find the Laplace transform of signal x of t is equal to u of t minus of phi. So we need to go for the solution using for the time shifting property of Laplace transform. So the given solution, the given value of this example is x of t is equal to u of t minus of phi. The Laplace transform of unit step function is represented as L u of t is equal to 1 by s. How it came? I will write here. So the Laplace transform of x of t is equal to x of s. So this equation is 0 to infinity x of t e power minus st dt we write. So now I take for the x of t is equal to u of t. So the u of t is equal to, we know u of t is equal to 1 when t is less than or equal to 0. Sorry, this is t, u of t is equal to, I should write here, u of t is equal to 1 and t is greater than or equal to 0 when t is less than 0. This is the way. So t is greater than or equal to 0 in the sense 0 to infinity. Okay. So I write for this equation is x of s equal to integration of 0 to infinity then u of t e power minus st dt. So u of t is equal to 1. The limit is present for the 0 to infinity. Already you know 1 e power minus st dt. So we do for the differentiation. This one is represent by the e power minus st divided by minus of s. So the limit is equal to 0 to infinity. So this case the upper limit is e power infinity, e power minus of s infinity minus of e power minus of s 0 divided by minus of s. Okay, so this value is represented as 0 minus of this value is equal to 1. So here divided by minus of s. So this is equal to these two minus are getting to cancel, 1 divided by s. So now Laplace transform of u of t is equal to s, 1 by s. That's why I write for here Laplace transform of u of t is equal to 1 by s. Now take for this statement using the time shifting property of Laplace transform, x of t minus of t0 in the Laplace transform is equal to e power minus st0 x of s. Now I take for here the in terms of the shifting case x term, Laplace transform of u of t minus of 5 equal to how many time that shift is going to happen, that much multiplication is going to happen here, e power minus 5s. Okay, here is minus, that's why we have the minus. Laplace transform of u of t, the Laplace transform of u of t is equal to 1 by s. Finally I wrote e power minus 5s divided by s. Okay, this is represented as a Shanti. Now what will be happen for here, the given sum is shifted version of u of t minus of 5. 5 position that t is going to shifting. So that's why it's going to multiply by the e power minus 5s, then u of t is equal to 1 by s. Okay. So next property, time reversal property of Laplace transform. The time reversal property of Laplace transform state that if a signal is reversed about the vertical axis at origin in the time domain, then its Laplace transform is also reversed about the vertical axis in s domain. So now we take for the x of t in the Laplace transform is equal to x of s, then x of minus t, the Laplace transform also getting to shifted for the minus of s. Okay, that will be here I state the statement, the time reversal about the vertical axis at origin in the time domain, then the Laplace transform also reversed about the vertical axis in the s domain. For the vertical axis of time domain is reversed in minus, then Laplace transform also vertically reversed for the minus of s. Okay, we need to prove for the statement. Okay, prove. The definition of Laplace transform we should write as x of t of Laplace transform equal to x of s equal to integration of minus plus p x of t e power minus st dt. Then by substituting t is equal to minus of t. Okay, this equation t equal to minus of t. I substituted for the t equal to minus of t here. Then where the t is present for x of t position only, I substitute for the t equal to minus of t. Now minus of t I take for the u, then dt is equal to du I make to write. Okay, so Laplace transform of x of minus t equal to integration of minus into plus t x of u. So here have the t, then t, this t is represented as a minus of u. I substitute a minus and minus getting to cancel, then du, dt is equal to d of u I write. Now I should re-modify for this portion only, integration of minus into plus by x of u e power minus minus, it is a plus, the plus is represented as a minus, I split it, minus of s u du. Then this term is here is how the minus of s, that's why I should write for the x of minus s. Now the statement x of minus t, that is a input domain, we should give for the negative, then output domain of Laplace transform also s domain is also negative term. The time reversal property is getting to prove here. Next, conjugate property of Laplace transform. The conjugate property of Laplace transform state that for the complex function x of t, the Laplace transform of x of t is equal to x of s, then x star of t Laplace transform is equal to capital letter X star and S star. This is a statement of complex conjugate property of Laplace transform. As per the case of Laplace transform definition, I should write Laplace transform of x of t is equal to x of s. This value I make to write for the both the directional equation minus into plus into x of t e power minus st dt I should wrote. Okay. Now what I am doing, instead of x of t, I should apply for the x star of t. Okay. So if I say that means x of t I make to take for the conjugation. Now in the terms of x of t place, I should replace for the x star of t. Okay. So x star of t integration of minus into plus into per here. X of t, here is how the x of t is replaced for the x star of t e power minus st dt. This term it will be doesn't get to change. Okay. Now what I am doing for now, this star I take it out for the whole star of whole equation in the Laplace domain. So if I take here whole star, then what happened for this star is going to apply for here. Star value is representation, it's getting to cancel. Okay. Then minus s star d dt. So I write for this equation as integration of minus into x of t e power minus s star t dt whole star. Then I should write this whole term is represented. This term here is a star is there. That's why as per the statement of x of s, here is s. That's why we write for x of s here. Then here is star. Then x of s star. This whole star I keep here. Now what will be happen? If you take for the Laplace transform of x star of t, conjugate value of x of t, then Laplace transform also getting to conjugate as well as of s domain also getting to conjugate. Finally, I wrote the equation x star of t Laplace transform x capital letter x star of s star. Okay, now we proved for the conjugate property of Laplace transform. Next, conjugate symmetry property of Laplace transform. Okay, so the conjugate symmetry of Laplace transform state that the Laplace transform of x of t is equal to capital letter x of s. The conjugation property of x star of t is Laplace transform is equal to x star of s star for complex x of t. Okay. Now we need to prove for this statement. Okay. By the definition of Laplace transform, x star of that is x s star. Okay. There is no star here. X s star is equal to integration of minus into plus t x of t e power minus star t dt. Now, if you write for the Laplace transform of x star of t, this is equal to, we should write x star and s star. Now, this star is not there. Now, this star I make to remove for here. So what the value? Where the s is present, then only is going to happen for the here complex conjugate value. So I should take for here x star. Here I removed for the this star. Okay. For the, as per the statement, L x star of t is equal to capital letter x star and s star. Now, based on this property, I should remove for here s star. Then what will be happen? Where the s is there in the Laplace domain, we should put for the star this one. So now, what is it? How can I write for the equation? Integration of minus into plus into x of t e power minus s star t dt. Here only the s. So that s we replace for the s star dt. Okay. Taking conjugate on both sides of above equation. Okay. This equation I take for the both side conjugate. So here also conjugate. So here also I make to conjugate. I write here. So this conjugate I keep here. X star of s star is equal to integration of minus into plus x of t e power minus s star t dt whole star. This whole equation I keep for the star. That value is equal to integration of minus into plus into x of t e power minus of s star sa t dt I make to write. Now integration of minus into plus into this value x of t e power minus st dt. This value is equal to x of s, where x of t is real according to the conjugate symmetry property of Laplace transform. X of s is equal to x star of s star. Now we proved the conjugate symmetry property. Next, time differentiation property of Laplace transform. The time differentiation property of Laplace transform, it states that the Laplace transform of x of t is represented as x of s. Now this x of t I make to do for the input side, I make to do for the differentiate with time. Then I should write for the d by dt x of t. d by dt x of t Laplace transform equal to s into capital letter s minus of x of 0 minus. This is represented as a time differentiation property of Laplace transform. That is represented as a first time differentiation property. When you differentiate for the x of t in the Laplace domain, the signal is multiplied with, output signal is multiplied with s into capital letter S, x of s minus of x of 0 minus. Proof. By definition of Laplace transform, the Laplace transform of x of t is equal to integration of 0 to infinity of x of t e power minus st dt. This statement we know well. Here I taken for the unidirectional Laplace transform. Now this term I do for the Laplace differentiation. Laplace transform of first differential d by dt x of t. This is equal to integration of 0 to infinity. Where the t is present, I make to apply for the case. So the here is d by dt x of t as a statement. Here I may apply for the d by dt x of t. Instead of x of t, I should apply for the first differentiation. I apply for the first differentiation here. So this term, in terms of x of t, I should apply for d by x of t divided by dt e power minus st dt. This is common. The integration also it's represented as a common. Now I make to use integration of a to b u dv equal to u v, the limit of a and b minus of integration of a to b u dv. This equation I should adopt for the this value, because of I consider with this is u, this is represented as a v. Okay, this is u, I consider represented as a v. So now u is equal to e power minus st and dv equal to d by dt divided by dv is equal to d by dt x of t dt. I should substitute this all value into this equation. So finally I got Laplace transform of d by dt x of t is equal to integration of 0 to infinity e power minus st d x of t is equal to e power minus st x of t limit of 0 to infinity minus of integration of 0 to infinity x of t e power minus s e power minus st dt we wrote. Yeah. Now again we can substitute for the integration with limit. Then Laplace transform of d by x of t, that is Laplace transform d by dt x of t is equal to, after substituting the limit, 0 minus x 0 minus plus s into integration of 0 to infinity x of t e power st dt. This value is equal to x of s. Okay, I should substitute for here s into this whole term. I write for s into x of s minus x of 0 minus. Laplace transform of d by dt x of t is represented as a first derivative is equal to s into x of s minus of x of 0 minus. It can also represent by d by dt x of t Laplace transform equal to s x of s minus of x of 0 minus. So we can generally, this is a first order differentiation. If we take for the general differentiation, that means n domain differentiation, I write d power n divided by dt power n x of t is equal to, that is Laplace transform equal to s power n x of s minus s of n minus 1 x of 0 minus 1 minus up to d power n minus 1 divided by dt n minus of 1 x of 0 minus. So that based on this case, I take for the some example. Using differentiation in time domain property of Laplace transform, find the Laplace transform of the function given as follow. The x of t is equal to del of t, we taken. Then x of t again I take for the d by dt del of t. First we should find for the Laplace transform of x of t equal to del of t. The given function x of t is equal to del of t as a solution. This is a first sum I take. Del of t is equal to d by dt u of t. We studied for the first model for the relation between the u of t and del of t. What's the relation between u of t and del of t? If you need for the del of t, you can differentiate with the time in the unit signal, then we got for the del of t. So I take for the statement because of we need to use for the differentiation in time domain property. So based on this condition, based on this rule, differentiate with u of t, we got for the del of t. Then del of t is equal to d by dt u of t, and the Laplace transform of u of t equal to 1 by s we studied. Laplace transform of u of t is equal to 1 by s we studied. I wrote for here. Okay, based on this condition, the time derivative property of d by dt x of t Laplace transform in the first differentiation s x of s minus of x of 0 minus. Now Laplace transform of del of t is equal to, we use for this equation, Laplace transform of del of t is equal to Laplace transform of d by dt u of t. So this term d by dt u of t I write for the s l of ut minus of 0 is equal to, so this s term I keep here, the Laplace transform of u of t is equal to 1 by s. Then these two s's are cancelled, then we got for the 1. Okay. Now the Laplace transform of del of t is equal to Laplace transform of d by dt u of t equal to 1. Okay. So first statement is getting proved. Second statement, x of t is represented as a d by dt del of t. Okay. Using differentiation property of Laplace transform, Laplace transform of d by dt del of t is equal to s Laplace transform of del of t. S into Laplace transform of del of t. Laplace transform of del of t is represented as 1. So I should make to write here. Laplace transform of del of t we make to write. So we know the x of t Laplace transform is equal to x of s. Now I should write x of s equal to integration of 0 to infinity x of t e power minus st dt we wrote. Okay. Now this, where the x of t is present, we should substitute for the del of t. Now we know the del of t is equal to 1 when t equal to 0. 0 otherwise we should write. Okay. Del of t equal to 1, t equal to 0, 0 otherwise. So based on this case, Laplace transform of del of t is equal to integration of 0 to infinity del of t e power minus st dt. But the condition is t equal to 0. Okay. 0, that is 0, t equal to 0, only 1 0, del of t equal to 1, e power of minus s t equal to 0 d of t. Now what is that? E of 0 is there. Then what the value we got for this statement is equal to 1. Okay. So now what I'm doing, L d by dt, this term del of t is equal to S Laplace transform of del of t as per the differentiation property. The Laplace transform of L of t is equal to, we find for 1, we substitute here S into 1, then this is equal to S. Okay. Laplace transform of d by dt del of t is equal to S. So now we straight to prove for the statement. Next case. Next property, integration in time domain property of Laplace transform. The differential equation in the time domain into an algebraic equation in the frequency domain of S or S domain. I say again, the differentiation equation in the time domain into an algebraic equation in a frequency domain or S domain is called integral in time domain property of Laplace transform. This means if we do for the differentiation in time domain in the case of input, we got for the output also in the Laplace transform we get for the differentiate with frequency domain or S domain. That is called for the integration in time domain property. As for the time integration property of Laplace transform, x of t Laplace transform is represented as x of s. Then I make to do for the integration of x of t in terms of minus infinity to plus t, x of tau d of tau is equal to x of s divided by s plus integration of minus infinity to 0 x of tau divided by s d of tau. So this means the integration in time domain, okay, for the differential equation in the Laplace term, the output domain also is getting to the integration of frequency or S domain. That's the statement. We need to prove for this statement. I consider the function is represented as y of t. The y of t is equal to integration of minus infinity to t x of tau d of tau. Taking the differentiation in both sides with respect to time. Okay, this equation taking differentiate with time with both sides with t. So this means d by dt of y of t is equal to x of t. Also y of 0 minus is equal to integration of minus infinity to 0 x of tau d of tau. Then the taking Laplace transform of d by dt y of t is a differential property. Okay, so what will be got? L x of t we represent. So this value, this case I write for the differential value of first differentiation s y of s minus y of 0 minus equal to this Laplace transform x of t is equal to x of s. Now at the same time, this term I should take for the Laplace transform. So y of s is equal to x of s divided by s plus y of 0 minus divided by s. That will be I wrote here. So this case I represent for this y of s only. Okay. So based on the equation I need for y of s. So what the y of s? This y of 0 is go for this right side. It got for the plus. This s is going to go for the divided by values. So that's why y of s equal to x of s divided by s plus y of 0 minus divided by s. Okay. Now I write y of s equal to x of s divided by s plus integration of minus infinity to 0 x of tau s d of tau. Okay. This term I should write y of 0 we used for here. Y of 0 minus equal to integration of minus infinity to 0 x of tau d of tau. So I should substitute here. Okay, this is I keep like this one. Now what will be happen? Y of s equal to Laplace transform of integration of minus infinity to 2 x of tau d of tau is equal to x of s divided by s plus integration of minus infinity to 0 x of tau divided by s d of tau. It can also represent as like this one, integration of minus infinity to t x of tau d tau. Laplace transform is represented as x of s divided by s plus integration of minus infinity to 0 x of tau divided by s d of tau. The integral property of time domain of Laplace transform is proved. Next case, frequency derivative property of Laplace transform. The statement: the differentiation in a frequency domain or S domain property of Laplace transform state that the multiplication of function by t in time domain result in the differentiation in S domain. Now, I should write for the Laplace transform x of t is represented as x of s. I multiply with the t into x of t. It's a time domain as the statement. Okay, I multiply with the t into x of t. The Laplace transform is represented as a minus d by ds x of s. The output side is going to differentiate with time as per the statement. We need to prove for this statement. From the definition of Laplace transform, x of t is equal to x of s. X of s equal to 0 to infinity of integration x of t e power minus st dt. By taking differentiation with respect to of s domain, I take for this one d by ds x of s equal to d by ds integration of 0 to infinity x of t e power minus st dt. Now, d by ds x of t is equal to integration of 0 to infinity x of t, where the s is present in the equation. Here only have the s. So that's why we make to do for differentiation with here only. So differentiate with a case of the equation integration of 0 to infinity x of t d by ds e power minus st dt. If differentiate with s in the case of e power minus st is equal to, that is d by ds e power minus st is equal to minus of t e power minus of st. Okay, we should substitute here. T in terms of this value, we substitute this one. So now the equation is changed as integration of 0 to infinity x of t minus of t e power minus st dt. This minus t and x of t we take it out from this term. So now I write as equation as 0 integration of 0 to infinity minus t x of t e power minus st dt. So now here is x of t, that's why I write for the Laplace transform of minus t x of t. Okay, this whole term I should write. So this is x. Okay, x place will be going to have here. Remaining term have the same. So the x term I should write but Laplace transform minus of t x of t. Now I should write Laplace transform of t x of t is equal to this minus go this side. Okay, left side. Then minus of d by ds x of t. So this is represented as here. If input side, if we are going to multiply with the time, the output side, the reverse with differentiate with the s domain of capital letter x of s in the Laplace transform. It can also represent as t x of t. The Laplace transform is equal to minus of d by ds x of s. As similarly, if I am going to have for the t square in the time domain, the result is what will be going to happen. Laplace transform of minus t square x of t is equal to d square divided by ds square x of s. Okay, if you have n terms, okay, if you have the n terms in the multiplication of input side, Laplace transform of minus of t whole power n x of t is equal to d power n divided by d of s power n x of s. Hence, it proves the frequency derivative property in s domain of Laplace transform. Okay, we take for some example. Using the frequency derivative property of Laplace transform, find the Laplace transform of the function x of t equal to t u of t. Okay, we receive the equation as x of t is equal to t u of t. Then the Laplace transform of unit step function we studied. So the unit step function is equal to Laplace transform of u of t is equal to 1 by s. By using the differential s domain, t x of t Laplace transform equal to minus of d by ds x of s. Now Laplace transform of x of t equal to L t u of t. That means minus of d by ds u of t is there. So that is represented as a Laplace transform of u of t is equal to 1 by s. Now the value is equal to, if you differentiate with s domain of 1 by s equal to 1 by s square. Now Laplace transform of t u of t is equal to 1 by s square. Okay, up to this much I'm going to stop this section. This all topic I refer from Signals, System and Communication BL Ethic and AV Openum, Signals and System for second edition. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.